Some people argue that brainwaves are the foundation of telepathy, that we do communicate through the electromagnetic spectrum. Here's a website arguing that alpha waves are typical of experienced meditators, that they're able to open their minds up to the signals of humanity and pick up resonances from all the other brains because they can train their minds to adopt alpha states. So here we've got various pulses, technique and attitude changes take place at alpha and theta levels of mind during guided meditation. The trouble is, if I asked you just to close your eyes for a few seconds, your brains would start generating a nice alpha pulse as well. It's what happens when we relax and close our eyes. Our brains go into an alpha level. As you get more and more asleep, your brains slow down and you go down into delta and theta waves. So it's nothing special. All it means is you're relaxed. But according to the Bodhisattva Sutra web page here, there's a quote on this page. When we say something to ourselves, an electrical potential is produced on the surface of the brain, which ranges between a few microvolts and a few hundred microvolts. That's all true. That bit is the science. What happens if we're able to convey this potential without using any language? This is the nature of telepathy. That's the pseudoscience. What happens if we could? Well, it would be telepathy, but we can't. Unfortunately, these people are using the science here to make a pseudoscientific claim that brain waves allow us to communicate the contents of our thought between different brains. And if we just think about the physics, it simply just doesn't hold up. Nevertheless, if you've got the right machine, you can pick up these brain waves. And this machine is called a squid. So brain waves, they're not picking them up because they're picking up radio waves, though. What they're picking up is another form of electromagnetic sort of wave that's produced by this neural activity. It's the magnetic fields that your brain generates. So this woman's not having her hair dried. That big machine is reading the magnetic fluctuations that's caused by her neurons firing. This is a great technique because it has extremely fine resolution. It can tell exactly which millimetre of your brain is doing the thinking. And it's got a very good timing resolution as well. It's doing it every fraction of a millisecond. So it's a very, very precise way of measuring brain activity on the surface of the cortex. But you have to have the right equipment. You've got to have one of these huge devices. And what SQUID stands for is Superconducting Quantum Interference Device. It's superconducting because it's cooled to near absolute zero with liquid helium. So it's not something you want to carry around with you. It's a quantum interference device because it works by those magnetic fields having a quantum effect upon atoms within the device itself, pulling them apart. And it's only this very small effect that it can have, because these things are absolute zero, allows the machine to identify what's happening. And as a general technique, instead of electroencephalography, this is called MEG, or magnetoencephalography. But at the moment, the finest grain temporal resolution that we can get is from advances in Berger's original technique of EEG. But now, instead of just having one electrode measuring the bits of the brain that he was using, we have multi-channel EEG. So here's a picture of someone actually in our labs, a participant, having a multi-channel EEG skull cap attached. We do these studies. You can volunteer to take part. You can be a participant in a multi-channel EEG recording experiment. In your final year, you could even do a project using this equipment to measure other people's brain waves. And the way they work is all these electrodes on the surface compare minute changes in electrical activity with a base current at the back of the skull cap. But it's a small current. The changes that take place are, as that yogic meditation site said, around plus or minus 5 microvolts, millionths of a volt, very tiny changes. We're not going to electrocute anyone with our brains. You plug these things in, you get a mass of data out, lots and lots of wiggles and activations that you have to use quite horrendously complicated statistics to pick up the signal, the wave, the response in the brain from all of the background noise in that signal, all of the other electrical activity, the muscle activity. And when you do that, you end up with something like this. Now, we're not talking here about nice rhythmic alpha waves and delta waves and theta waves that are transmitting our thoughts across huge distances. This is what's known as an event-related potential, or ERP for short, where on the left here we've got a stimulus being presented and then time passing. Now we're talking about half a second, so this isn't just the pulse from one neuron, this is the pulse from a whole assemblage of neurons all working together. And when you add up all the activity of all of these neurons, you can see how they process the information that's been presented to them. And you get a characteristic pulse. Around 100 milliseconds, we get, first of all, a positive dip and then a rebound of negative activity. Now, it's an oddity of the way that these things are plotted. Positive is below the line and negative is above it. If you become an electroencephalographer, you'll get used to it. For now, just remember that positive is below the line and negative is going up. So you get this positive at around 100 followed by a negative potential. That's indicating that a stimulus has arrived. And then we start to process it. And there's another little positive-negative transition around 200 milliseconds, and another one sometime around the 300 to 600 millisecond. The first sort of 4 wiggles are pretty characteristic of any stimulus coming and being processed. But what happens after that is really interesting and depends upon your interpretation of the signal. And this is what is causing major interest in how we can actually detect what's happening in people's brains. If we look at it over the whole brain, so here's the whole multi-channel recording sort of mapped out in space. Someone looking at this can see that the P, the posterior, again, we know what that is now, that's the back of the brain, and the anterior, the front of the brain, are doing different things. There's a huge peak in the signal here in the P area compared to the A area where it's lots of little wiggles. Now, you know that the back of the brain is where the visual cortex was. We saw that in the left brain, right brain lecture. So this probably means that this person has just had a visual stimulus presented to them and they've noticed it. Both hemispheres are showing that big peak. So we can see what they're thinking about, if you like, from the pattern of activity across the brain at that instance in time. A visual stimulus. So that's what they're thinking about, if you like. And this signal that happens, this late sort of P3 it's called, or P300, this positive dip that happens around 300 milliseconds, was first sort of categorized in the 60s. It's the largest bit of the EEG signal in terms of voltage, but you can see here that it's coming down to about plus 6 microvolts. It seems to signify a match or a mismatch with the contents of something that we're consciously maintaining in our working memory. So it's almost like finding out that it's a target you've been waiting for. You've been holding this thing in mind. I show you a stimulus. It's what your target is. You notice it, you press the button. But even before you get to press the button, you will have shown this P300. Confusingly, it also seems to fire off when you get something that isn't what you've been waiting for. So it seems to indicate this recognition decision time. It seems to be something to do with updating working memory. It's almost like a bit of information going into the pigeonhole. But it's such a characteristic signal down here that we can use this to detect people processing information after we've shown them a stimulus. There are now more refined versions of this, and you can see how it could be useful for someone who was severely disabled, who was in a wheelchair, who was completely paralysed, for example. They could look at their keyboard and it could light things up in progress. And this woman perhaps is looking at the letter S on her keyboard. It lights them up. When the ASD is lit up, her P300 peaks. The computer says, oh, it was one of those three letters. And then it will just go ASD, ASD, until it detects another P300. And she might be able to type at the speed of a letter a second, or every 2 seconds, which is easier than some of the other systems that paralysed people have for typing today. So this woman has managed to type, simply by looking at the computer screen, BCI, which stands for Brain Computer Interface. These are now commercially available systems.